Yes.
Right.
Yeah. Okay, good morning.
I might not wish to be here.
Welcome,
Oh,
and in many cases, welcome
Right.
back to Condensed Matter
yeah.
in the city.
Move along a bit more.
I'm just looking through, and the first Condensed Matter in the city began on the 5th of July 2010. So, so this is technically, you can do that the 15th time, but it's only the 15th time in person. Amazingly enough, we only lost 1 year during the pandemic. We actually kept on rolling the whole time. And many of you will know that next year is the 100th anniversary of quantum mechanics. If Condensed Matter City had been held 100 years ago, it would have spanned the entire time from the discovery of the Rutherford atoms to the beginning of quantum mechanics. We have not accomplished that. But on the other hand, there would have also been a world war in between. So we avoided that part. That was good. I want to thank all the people who are involved in setting this up. It requires a whole family of effort to make Condensed Matter in the City work. There's our team of Sam Carr and Gunnar at Kent. This is an event that is held amongst the Hubbard Consortium. This is a group of theoretical physicists in the general London area, UCL, Imperial College, Kent, and Royal Holloway University of London. I hope I haven't missed anyone out there. We get together every year starting around December and start planning the next year ahead. And it requires quite a lot of effort. I want to thank everyone who's really been involved in that. We also have managed to get support in various years from the IOP and also very importantly from ICAM, the Institute for Complex Adaptive Matter. One of the things we do at these meetings, and it's very important to start off as we plan to continue, is to ask lots of questions. Every speaker is given 1 hour and 20 minutes, but that really means that we're allowing about 25 minutes for questions during that time. And we encourage interruptions and questions. There's no stupid question. This is what a certain folder of stupid questions. If you use it up, you have to stop. And so we really do benefit from the sort of informal atmosphere of discussion that goes on here. And it's a chance for young people to meet people in the field, ask questions, get to know things, make connections. And I think from the first Condensed Matter City, some of the people who came to that are now faculty members. So think of that, some of you will be in 15 years' time. Without more to ado, let me introduce you to Professor Ali Yazdani. Ali is one of the world's experts in scanning tunneling microscopy. He has received many awards for his groundbreaking work. I guess the Buckley Prize in particular. He's an academician, so he knows stuff. And he's going to share with you his marvelous new work on two-dimensional electron gases.
Thanks very much, Piers. Good morning, everybody. It's always a pleasure to be back here in London, and especially this meeting. It's a fun meeting to be at. I'm going to talk about two-dimensional systems today. I'm going to talk about visualizing, installing in electric states and in electronic states, flat bands. So I'm going to just get right started into it. Of course, as you know about this, the multi-state is for us, starting from building of land elements and giving us fraction of the whole state. And more recently, as you know, probably, we have come up with a new way to those flat bands using basically twisting of two-dimensional systems and using the Wallach potential as a way of creating band structures in which you can mimic to some extent the features of the land element. These bands have both flat in energy and also Chern numbers, even though they're not breaking numbers symmetry. So, and there have been a collection of exciting things coming out starting with the work on looking at insulating, correlated insulated and superconductivity, magic and graphene, to even more recent work that has to do with finding fractional term insulators in moly and telluride stacks of twisted material. So our goal in our team is to try to understand the nature of these correlated states, topological and superconductive states, and do this using the local flows, in particular scanning from the microscopy. Sorry, part of this screen has to be always at this block. Giving you
No, you can turn it up. You can go to more. Yeah, and then yeah, I think that's probably it. Good. Yeah.
Okay, thank you. All right. Okay. Yeah, so today actually my goal is since I've given an hour, I guess, to speak with your interruptions, I'm going to actually present a lot of data having to do with experiments on both systems, both twisted magic and graphene, and also land on physics in straight untwisted material. So let's just get started with magic and graphene. So you twist these two layers, you get these flat bands, and we can think of them as a conduction and a valence band, which are relatively flat, about 10 or 12 million electron volt in width. And then they have Chern numbers, these bands, positive and negative Chern numbers. And when you half fill them, you get an insulating state, and this would be your discovery, which was first thought to be a hot state. I will show you not a hot state. But then you don't get insulating state and you get a superconductivity. The nature of this superconductivity and this resemblance to all these different correlated superconductivity. It's sort of a minimal model that gives you how complex this problem is. It's called the Carter model, which assumes the bands are completely flat. We just deal with the spin and valley and Chern centricity symmetry of this problem. We find that basically you have 8 flavors of electrons, and the question is, if you look at half fill this band, what kind of ground state? So there are lots of possibilities. And you can make a lot of different kinds of states having to do with valleys, spin, so the first question that I want to answer in this talk is a question of half filling of, say, the valence band in the system. And you have basically you have 2 electrons in this flat band, and you ask what kind of ground state. And then after that, we talk about superconductivity. So let me show you what we see when we start to create these samples and use SDM to study them. Right away, let me just tell you, it's very difficult to make very big samples because the way these materials are made is using tearing and stacking of conventional materials. So stacking them, like to pick them up and put them down, essentially involves polymers. And polymers is glue, and this glue is very detrimental to any kind of atomic microscopies you think you want to do. Our transport columns basically sandwich these things inside for our nitride layers. You don't really look what's there, and you just stick the leads on and make it the bank. So you don't have the luxury of not knowing what we are imaging, what we are studying, because we have a microscope. So we have spent a lot of time to create extremely clean samples, as you see. So what you see is in the topography, first you get structural information. For example, you see that there is different regions of stacking, which gives you AA and AB stacking of the 2 graphene layers. From the images directly, you can measure the twist angle because essentially the Moiré periodicity, which is the bright spots, I'll tell you in a moment why they're bright, essentially tells you what the Moiré wavelength is from the image, from which you can get the twist angle, provided the Moiré is not straight, which is a subject that we will talk about a little bit as we go along. Now, what you see in the SDM images are these, you see a lot of information. So you, for example, in this last image, on the very finest scale, you can see, people try and get it. On the very finest scale, which you can't really see on this projector, you see the carbon atom. You see another Moiré structure, that's the BN that's underneath. the sample that have an moray structure with the physical bilayer graphene, and then you have the moray on the larger scales between the two graphene layers. So you get all this information from the images. Now, when you do spectroscopy, you'll see the flat bands in spectroscopy, but even in the images, these bright spots essentially come from the fact that the electrons in the flat bands are localized in the AA regions. This is essentially the interference effect that gives rise to kind of semi-localizing electrons in the AA region in real space. And this will become important as we try to think about interactions, for example, in this problem.
Question?
Yes,
In all of your experiments, you have an exposed top layer,
that's right.
And-
Yeah,
and-
back to
and you have your BN beneath. Is there any reason to
graphite cap.
suppose that asymmetric setup is different to what you get when you
Yes,
just
that's right.
coat it on both sides?
Yes, so the electric environment is less, so interactions will be stronger in our experiments.
Yeah.
And typically in the samples that I show you, our gates are a little further away than our transport columns, just the way our samples are made.
Mhm.
So essentially, we're looking at a
Stronger.
situation that interaction is even stronger.
Even stronger, yeah.
Okay, so it's a busy slide, but let me walk you through it. So let me go back once. So you can do spectroscopy. Remember, in STM, you measure the timing density state, the IBD as a function of sample to bias. And there is a gate here, so you can adjust your gate to fully occupy the flat bands or completely empty them. And these two sharp peaks are the Van Hoff singularities of these flat bands. From the width, you can sort of see that there are about 10 or so milli electron volt. This is very sensitive to the strain in the device. Okay. But you see that they're sharp. Okay. And what is interesting, the first thing we discovered in this field is what happens as you start to partially fill these bands, and all the spectral properties of the flat bands become extremely broad. So this plot is supposed to be read like this. It goes down, back up, and down, back up. So you can see that there are these two sharp peaks, and the sharp peaks are being tuned to the chemical potential by the gate voltage. And then as you reach the chemical potential, they become extremely broad. And then they get a little sharper around charge neutrality, and then broad again. And then when they exit the region near the Fermi energy, they become completely unoccupied, they become sharper. So let's look at the data here. So these three lines here. So this is just all this information plotted in the color plot. These two lines are the two flat bands coming. These features are these broad features, and then this is where the flat bands exit. A way to bring out the features is to take the dIdV and divide it by I over V. And this is because when you do experiments at every gate voltage, the tip heights may be slightly different because the density of stable section is slightly different. That takes it out of that normalized thing. So what you discover is that there are cascade of features in this data, much sharper here and then over here, at every quarter filling. And this is an experiment that's done at very high temperature. So this, if you want to think about this, is the normal state of this twisted bilayer graph. So right away, we can just look at this raw data. This is something we could never do in any other correlated system, to tune it between the non-interacting picture and an interacting picture by just changing the grid voltage. Fill the bands, partially fill the bands, see what happens. So we were very excited about this at the very beginning because it showed us that we really can see effective strong correlation in this process. So now you start to ask, what are these features we see? So the first thing we did was kind of made the dumbest model possible, which is just look at the STM image, and what you see are these red bright spots. And basically tells you, oh, electrons are living here. So just treat it like a quantum dot, very weak hopping, and on-site Coulomb repulsion. This is just a decoupled quantum dot, and you can basically solve this problem. And you have basically two sharp levels in the quantum dots. The two flat bands are just two levels, Z0 minus Z0. And let's turn off T, and you have large U. And you can ask, what would the additional spectrum look like in the quantum dot with the number of flavors that we have in magic angular graphic? This is 8 levels of electrons. And you kind of can see a resemblance between these two pictures. And what it is telling you, these cascade of transitions, has to do with just the Coulomb repulsion filling having electrons live inside these. Now,
Question?
this picture more recently has been considerably refined and connected to sort of heavy electron physics by Andre Vernovic and collaborators. And essentially what they have done is they have shown that this Fitzgerald-McDonald model which is how we came to understand the formation of flat lands to begin with, predicted the formation of flat land to begin with, can be kind of understood as localized electrons living on, we call it F electrons. I didn't read this term.
Flat.
Localized electrons. These are not F electrons. And then couple that to bilayer graphene, and bilayer graphene that's not untwisted. And essentially, you can recover this whole picture. So this is quite a nice way of constructing this problem. And now they are doing calculation within this picture, and you can kind of understand what we are looking at in our experiments is sort of semi-localized electrons giving you these formed up pictures, because you have a lot of electrons localized in these sites, and then you have itinerary.
Can I ingest that?
You're running out of your.
Can I inject some healthy skepticism here, even though I like the model very much? If you make up an estimate of U based on the dimensions of this Vanier state, and you put a huge amount of screening in, you get it down to 50 millivolts. But actually, the raw number is more like 100 millivolts, especially for your geometry. So there's a big difference between what you measure as U and what's predicted from the ab initio point of view. And I wonder whether you have thought about that.
I have.
Yeah. Okay.
I have to think about it. But
Yeah.
You're right. From the experiments, this kind of toy model experiments, you can get some numbers like 25 millivolts for you to match the features of this data roughly.
But you can also plug into your wave function and estimate how big U is, and there's a big difference. Yeah.
This is where that's when we
Okay.
the experiment. And this number is actually not that inconsistent if you think about two electrons living roughly a Moray distance apart, not using wave functions, putting the gate not so far away, and screen that interactions. This number actually is close to that.
Yeah. I don't agree.
Okay.
Just wanted to inject that in. I think there's a big discrepancy. Okay. All right.
Yeah, of course.
Is there, from your experimental data, is there some typical anything that you could use that you can expect something that you say for the
Okay, so now you're getting into the question of whether there's a quantum physics of this problem and so on. And we haven't looked at that, but let me just we haven't done those experiments. But if you take this picture, so you can take a different picture, which is I guess this is done by collaboration of folks who have been taking a near margin calculation and try to compute sort of spectral function, just like our experiments do, using such calculation. They also recover some of the features that we see in the data, and in particular, what this field has focused on is these what we call this cascade of transitions that happen before filling, and this has to do with, it looks like the system resets itself every quarter filling, so there might be some quantum physics near even immature filling at very high temperatures, and this requires sort of further experiments to really prove. But I wanted to just show this as saying, this is essentially showing that the normal state is for sure strongly correlated. There might be some quantum physics in the normal state, but there's sort of local physics of electrons living on this AA site and talking to each other through conduction like electron. Okay, so now with that sort of introduction of the normal state, let's cool the system down and ask what kind of insulating state that superconducting state. So the picture that I showed you before, as you cool it down to millikelvin, this is 200 millikelvin, you start to see features. Actually, those cascade features that can go away at very low temperature, and they're replaced with. And this might be indicative of some screening quantum-like physics problem, but they're replaced by particular fillings, and we should see very sharp gaps. So this particular is a half filling the valence stands, okay? So you have 2 electrons per Moore unit cell inside the lower band, and you see a very sharp gap. And this gap opens and closes, and then another gap opens between -2 and -3. And I didn't include that in this talk, but we've done a lot of experiments in this regime of gating to show that this is actually a superconductor. And the way we have done that is by using a wave reflection with the same kind of device where you push the tip into the sample and see that there's unwave resonances which basically can be killed with the magnetic field and temperature in this gate region. So this gap coexists with superconductivity, and this gap is not superconducting because there's no unwave signal at these regions. I don't have the data here, but if you're interested, I can show. So obviously, you can look at the superconducting gap in the same instrument. You can put a piece of aluminum, which has TC of 1 Kelvin, and measure its density of state. You get a nice BCS density of states, S-wave gap. But in this system, that's not what we get. You get a V-shaped density of states, which is indicative of a nodal gap. And if you try to fit it with your S-wave model, you have good broadening that's just obvious. So right away you will get some. If you interpret this gap as a superconducting gap, which will not be, you would measure a 2 delta over KTC of 25.
Wow.
Parts. Okay, so this is kind of the extent of what we know about the superconductor at this point. It looks like it's nodal. There are some new experiments coming out by other groups that suggest that this is actually true because they're measuring superfluid density to temperature, and they're finding behavior that it's not systemic S wave, it's more consistent with a normal superconductor. That's pretty much all we know at this point.
Does this gap survive above the superconducting temperature?
Good question. Next slide. How does it survive? It does. So it does have a pseudo gap-like behavior. So as you go up, this is at 4 Kelvin. You can kind of still see it. This is in the gate range where you have the gap at low temperature. But more interestingly, in this system, this is not like cuprates because you can really kill the zero resistance states completely with just a Tesla. And you can stay at the lowest temperature and measure the spectroscopy, and you can see that this gap is very much doesn't care about the presence of global superconductivity as far as zero resistance goes. So take this however you like. This is a freeform pair. I don't know. Is it another kind of order? Maybe. And that's you'll see in the later part. Or this is something to be designed.
How does the coherence length compare to the penetration depth? Is it type 1 or type 2?
This is a type 2 super.
It's definitely type 2. So is it, okay, sure.
Is there alignment with boron nitride?
This is not aligned with boron. When you align with boron nitride, you kill superconductivity. And that's actually very interesting. That's one thing we found. But when it's aligned with boron nitride, it kills.
Experimentally, if you move the tip to another equivalent site, is the data reproducible?
Yes, it's highly reproducible, and actually compared to cuprates, this is a highly homogeneous gap. There is no doping homogeneity in the system. To speak of, there is twist angle homogeneity, which is there, but we can kind of see correlate that and stay away from those regions. Okay, so now let's go back to the other gap, the insulating gap. So there's been a zoo of theoretical proposals. Okay, so, you give the theorists a bunch of degrees of freedom, they run amok, they come with all kinds of exotic states. And actually, I have to say, in this case, the theorists were ahead of the game, and I'll show you that they found things that turn out to be true. Okay, so here are the zoo of states that has been proposed for the new ±2 or all the different disciplines. At the time that we got started, I think this state, KRBC, which has these symmetries and these broken symmetries, was one of the leading candidates for the insulating state. And a highly exotic state with actually loop currents in it was this. That turns out to be not the state. So how do we find that? So again, as I like to, to our point, we work very hard, we make very clean samples, and this turns out to be key. There's no other way to solve this puzzle unless you make samples that are ubiquitous. I think this is sample number 250, I'm not joking. And what you see is, on the finest scale, you can see the atomic size of graphene, and here actually you see other things that I'll get to. And you go out to this large 50 by 50 nanometer, which may not seem like a lot. This is like 100,000 atoms there. But there is not a single atom out of place and not a single adsorbate. Okay.
Wow.
Which is kind of crazy. I never thought this was possible. I don't want to venture this too hard, but we studied helium for a long time, right? And we learned so much physics by studying helium. Now I'm going to believe it that maybe graphene could become a system where it could be like helium. It's so clean that if you produce a lot of electronic states in it, like we are doing, you can learn a lot of physics from this very chemical process. Okay, so what do we see when we get these clean samples and we look at the insulated gas? So this is data at slightly higher temperature, but it does the same thing at lower temperature. I just wanted to show you the evidence that was all consistent as a function of phase voltage. In a small field of view. I'll show you the lower temperatures. So here, the blue line lights up where we are taking an image near the Fermi energy. This is a metal. And then as we, on Fourier transform, you just see the graphene. Now, this is a very small field of view. And as you start going into the insulating gap, you begin to see other features. And you see that there's this tripling of unit cell that happens from all these graphs. Sorry, this a little bit so the tripling of unit cell happens by these red peaks, and it's so ordered that you can see even a higher order peaks. And if you exit this insulating gap, so you can correlate the appearance of this tripling of unit cell with the appearance of this insulating state. So when we measured this the first time, actually this was measured maybe 3 years ago, we were like, oh, this is wonderful. We figured out what the insulator is. And the reason we thought it was wonderful because it related to something we had studied in graphene just the year before, not in zero magnetic field, not twisted, but with the magnetic field applied to you make the zero magnetic level graphene. Zero magnetic level special. In graphene, you have 4 degrees of freedom, 2 spin and 2 values. And when we have filled this zero magnetic level, nice flat band, you also get an insulating state. This was discovered in 2010, and it was a puzzle as to what is the nature of this insulator, and we argued for a long time. And we came in kind of late to the game, but we basically imaged the states of this half-fill Landau level, and we found that it makes this tripling of unit cells a calculated state. That's what it's called because this is the occupied state, this is the unoccupied state, they're sort of complement of one another. And what you see is they're lining up the electrons along the bonds between the carbon atoms rather than on the bonds. And this comes about because in graphene, you have 2 valleys, and when you make a quantum superposition of these 2 valleys, you line up the electrons on the bond. And you can think of this on a block sphere, just like I did showed you on the previous slides for this magic graph. Here you just have one block sphere, and the ordered state is one in which you make a concurrent superposition, and this represented by this vector. Now, interestingly enough, and this is going to come later in the talk, depending on what is the orientation of this angle, the density of space in real space can actually make a difference. So this we discovered in modeling graphene.
And just to be sure, K and K prime are valley indices.
They're valid.
So what's happening with spin and other things in this case?
So in this case, the field is large. So this is
I see. Just I see. Okay.
We don't have an external.
Got you.
So of course we saw this tripling of unit cell in magic angle. You see a twisting of unit cell here. We said, okay, it's an intervalley coherent state. Congratulations, let's write a paper. Except now you start digging and get more data. So as the samples, sometimes somebody told me publish quickly so that when you learn more, you can publish another paper. had to do the opposite, so it becomes extremely painful, and this is what happened in this project. As the samples got better, so this tripling of unit cell, the pattern was changing in space. And as the samples got better, at first we thought this was just due to disorder. As the samples got better and better, we saw that the tripling of the unit cell had patterns where it was changing in the field of view, which was very reproducible from sample to sample. Slight changes here or there, but they are highly non-trivial. So here was one I showed you before, and here's one where the unit cell is tripled, but now it's sitting on the carbon bonds, and here it's sitting somewhere in between. So this was like a mess. It was like you have tripling of unit cell, but it's like varying all over the place. So what the hell is going on? So this is what's working with our theoretical colleagues is very useful. Mike Zalatal and his students. So Mike had worked with us on this half-wave band problem. And in that problem, we had seen some variation in space, and we had learned how to analyze this information, which I won't get into. But here we apply the same technology. So the idea is the following. You take very small field of view, you take a Fourier transform of the data. So you have two sets of peaks, the atomic peaks, and you have the calculated peaks. And you have both the amplitude and the phase information, okay? And what you do is you represent this, on all the possible ways in which you can get density patterns on a graphene map. So you go to the basically the irreducible CT representation. You have 6 complex numbers that describe everything in the data. Okay? And we are most interested in this intervalley coherence order, which is represented by these 3 complex numbers. So the way to understand these 3 complex numbers, for dumb experimentalists like me, is that you can think of the SDM pattern as being kind of a combination of 3 different types of IBC. One in which you have density of state on the bonds, it can have its own phase, it's complex order. You can actually put the density of state on just one of the 2 sides, A or B cell lines. And you can vary the phase of that. So these are all the possible ways in which you can play tripling in cell. Okay. So what you do is you take data like this, and you bin it up in small little regions, and each region you extract these order parameters. So this sounds simple, except it's very complex, because you need to make sure that the center of the hexagon when you do your FFE, one corner of your image knows exactly where the center of the hexagon is in the other corner of the image. Otherwise, the phases do not mean anything from one place to the other. Mm-hmm. So this took a lot of difficult work to find all the atoms in this picture first, and a lot of coding by the theorists and a lot of checking by experimentalists. The result of which at the end was that we could extract these order parameters. And now what I'm showing you is one of the order parameters, IBC bar, IBC total. This just represents the total order parameter of having any kind of IBC order. So that's its amplitude. You notice that it's white, it's positive almost everywhere. And if there are some spots where it's suppressed. And then you look at the phase. Now you realize why this was such a hard experiment, because the phase is actually changing in real space. It looks very psychedelic, I know, but if you just focus in, you can kind of see that it's just going through phase rotations. And every, about 3 Moray units. So this is a phase, this is an electronic phase that breaks a symmetry, not just on the graphene scale. It makes an object, it makes an order parameter, and that order parameter can break the symmetry on the Moray units. And
this is happening spontaneously.
This happens spontaneously. And if you warm it up and cool it down, actually it forms the same way. So we can get into what strain has to do with it, and that actually is an important part of this.
So it's not spontaneous.
No, you can have spontaneous symmetry break in the presence of any kind of other perturbation. You might choose some direction.
But the strain is crucial.
Okay. So it turns out, and this is sort of the punchline of this whole thing, is that there are many nearby states. And if we choose one state over the other, turns out that this state is the one most favored and is found theoretically. We can have even in small amounts. Okay, so if you look at this data, there is this phase gradient. So I asked the students to basically subtract the plane of phase from this data. And what they discovered is that underneath that phase gradient, there are actually, if you remove that, there are these objects that looks like vortex, anti-vortex pairs in this IBC order. And now you can kind of see, I think it's like this. Now you can kind of see what's the meaning of these dark spots in the IBC order. It's just like a vortex. So the order parameter is suppressed at the core of the vortex and is winding one way or another if you zoom in into data So these are very, we have conceptualized a lot of things out of the data. Data has this real space patterns. The real space patterns represent these order parameters, and these order parameters can be extracted from the data. And it looks like, there is this lattice of actually putting codes, vortices and anti-vortices in these order parameters.
So these are the same, extracted from the same image, right?
It's all from the same image.
Is there a reason why the circles on the right, on the left are tilted vertically, whereas the cross and dots
These are
very
so these are the phase gradients subtracted from it, but it looks like the location of the holes is the same place, whichever.
okay? So it's just an optical effect or something.
Although you mentioned the importance of strain, is there a way of tuning the strain?
All that talk is coming in a moment.
Okay, thank you.
Okay, so I think these theoretical groups from Oxford and Berkeley, I think can take a victory lap because they were the ones who basically predicted this state. And the reason now we know it's this state, we went and calculated from the theoretical calculation what would be the real space maps of this IKS state. And I put it through the same analysis, just like it was data. And essentially recovered all the same features that we got from our experiment, including these vortex anti-vortices that they didn't even think about that was in their data. They didn't take a plane subtract of this. So what is happening here is, and also I should say there is another experiment on trilayers from Stefan Najpergi's group at Caltech, the STM. They don't do the same kind of analysis that we did. They do basically just grid Fourier analysis. They also claim a very similar finding of these states, this IKS. So what is this IKS? So you have one monolayer of graphene. In the magnetic field, you have just one block sphere. You have valley up and valley down. Now you have two. So one churn up, one churn down. Okay, so you have two block spheres of graphene. So you could make a state into a valley coherent state in each of these sectors, each sector by itself. Or you could do something cool. You can make another block sphere, which is a superposition of the other two block spheres. So what's represented here is creating a coherent state of the two different churn sectors, which are intervalley coherent sites. It's kind of a very, very weird state. And now when you make this state, if its order parameter can vary in space, it creates these breaking of the moraine. And actually the theorists using Hartree-Fock, I don't know, you can argue that you put the lead Hartree-Fock in this world, but using Hartree-Fock, they came up with a number around 3 unit cells, which is roughly what we have found. Strength. 95% of the sample we studied show exactly this behavior.
Question, just what KA and KB, what does A and B refer to?
A and B, so you have talk about
Just the last view graph. Yeah, there.
So
What does the comma A and B refer to?
it's the two different it's the two different, you have to go to the moray unit cell.
Yes.
And then you have to also talk about the graphene A and B sublattice.
Okay, sublattice. Okay, very good.
So in a few samples, number maybe 4 or 5, we can find that it has almost no strength. So how can we tell whether there's strength there? Is by just looking at the moray triangular structure and judging whether it's perfect or not. If it's not perfect, if it's elongated in one direction, we can make a model and say, okay, one graphene lattice is stretched relative to the other, and this makes the triangle a little bit different in the structure. But there are cases where we find that they're almost perfect. And those devices actually behave differently. First of all, at the textures of the
Yes, audio should be on. But you have to turn off your audio, otherwise we won't get.
my audio as well.
Okay, so since I have a little bit of time, let's go back in time and go back to the good old flat bands of the magnetic field. It's kind of interesting because we were very interested in using SDM to study, fractional quantum Hall states. Then magic angular graphene hit, and then we started working on magic angular graphene, and then we figured out how to make these very clean devices. And this actually made experiments that I'm going to tell you are possible in just regular graphene or bilayer graphene, which wouldn't have been possible without these advances. Okay, so I want to remind you of sort of probably the oldest correlated problem there is around, Wigner crystal. When you have low density, get electron forming a crystalline lattice spontaneously. And of course, as you know, with the magnetic field, the localizing electrons further in Landau levels should make Wigner crystallization observable over a larger density, as you would have in comparison to zero magnetic. I always encourage the students to go back to read original papers. If you've ever read the original discovery paper of fractional quantum Hall effect, they actually thought they had discovered the Wigner crystal, not the fractional quantum effect. I mean, these days, these guys would be all, thrown out, or I don't know, paper withdrawn, or I don't know what would have happened to it. They wrote a paper, they misinterpreted their data, but the data was exactly. So mistakes
suggested.
Well, anyway. And the story of looking for Wigner goes back to all of this physics, and actually starting even before that, people looking at the electrons on the surface of helium, where they found evidence of resonances associated with crystallization. This is a classical Wigner crystal. And looking for a quantum one, there are 1 million papers literally on this in this field. This is one of the prominent one by Eva Andre, using kind of similar technology to find resonances having to do with the stiff structure that's absorbing things. So, I mean, not to belittle all this excellent work, but, nobody's ever imaged the Wigner crystal. There is some work looking at what they call generalized Wigner crystal in a Moiré structures, which I forgot to put in the slide here, but more recently. But that's not a Wigner crystal because you just have a Moiré structure and your electrons are just localizing inside this periodic potential. It's not spontaneously forming, and it's not a continuously tunable order. So let me go through this relatively quickly because we don't have a lot of time. So here is a bilayer graphene device. It's not twisted, but you have the boron nitride Moiré are still there. And we cool it down. We apply a large magnetic field. I won't go to the details of the system, but n equals 0 and 1 are kind of nearly degenerate in the system. And the first advance that I want to point out here is one where you see this is spectroscopy. These lines are all Landau levels. And what you notice is that so the Landau levels are just like flat lines, like they should be. But before these experiments that we performed, every time people did STM on graphene or bilayer graphene, you do Landau level spectroscopy. So to do tunneling to a Landau level, you have to apply bias. So when you apply a bias, it turned all these previous studies showed something that was very kind of reasonable, which is that you apply a bias to your tip. Of course, you're going to gauge your sample. So essentially, all these Landau levels will become tilted as you try to probe them, and that made a lot of sense. Except when we start doing experiments, we realize our Landau levels are flat. We're not getting the sample. So this is kind of like good hygiene. I hate to say it like this, but you should have good STM hygiene. And the way we prepare our tips is that we know where our tip has been. We clean it on a piece of copper, and it turned out that this practice serendipitously gave us a word function matched tip to that of graphene samples. Carbon and carbon, these tips. Yeah, these tips have very close work function. We can actually see work function differences between the tip and the sample. We can actually use the lambda levels to measure it. And also we found, just experimentally, if you make the tips extremely sharp, they can't act like a gate. They can act like an impurity. I can go into the details of what they might do to locally put like an impurity potential. Very small one, the sharper the tip. And it just works. And we have a hard time publishing these experiments because people were saying this is not possible. Because look at all this list of references. These are all papers published by these great people. All their lambda levels are tilted. What did you do? Okay. Now, even more exciting. So let's zoom into one of the lambda levels. This is the 0 lambda level. And so you're tunneling near the chemical potential. What you see is this region which is dark. This is the Coulomb gap. So remember, we have a large magnetic field. So if you want to try to add an electron into the system, everybody's got to get out of the way. And this was discovered in gallium arsenide by Jim Eisenstein. And what you see are all these jagged features in the data. So these are all the fractional quantum Hall states. And as you tune your gate voltage, field is constant, 14 Tesla. As you tune your gate voltage, you're going through the different sequence, and you go in and out of incompressible states. And when you go in and out of these incompressible states, essentially you see an additional energy that goes into the tunneling to get an electron in and out of the sample, which reflects the presence of the incompressible fractional quantum Hall state. I won't bore you to this because I want to show you, well, that's actually not boring. There's a lot of physics to discuss there, but I just want to show you imaging. So I'm going to tune the STM tip bias to just at the edge of the Coulomb gap, where you're just beginning to put electrons into the sample. And we make an experiment where we plot in real space how much current is going into the sample without actually measuring conductivity. We're just actually measuring current. And this experiment is done with open feedback loop, meaning you're not adjusting the height of the tip, so it makes it kind of more exciting, dangerous because you could crash. But you can do it if you have a very stable instrument. And what you're looking at is what this current looks like, whether it's enhanced or suppressed, which is enhanced is red, blue is suppressed, at very low filling of this lambda level. So this is 1 is when you have the filled lambda level you can see. So let's watch the movie where we tune the density. And as you'll see, as you start to pack more electrons into this lambda level, there are these structures emerge in the data. And what you see is a very organized structure in which at some fillings like here, you have extremely organized lattice, and then 333, remember what that is? That's the Lofgren state. You get craziness, then you go back as you feel the density, and you see organized structure. So there's a lot in this data set. So let me run the movie again. And I'm gonna focus on a couple of things. So you'll notice that there's chaos at the beginning and low filling, but then you can see that there are some places where it looks like there's a defect in the data. You can sort of see that there are regions that clearly looks like you have an object that looks blue there, looks like a ball. And then there are places where you go to the fractional quantum Hall states where things disappear and they come back. So yes, this is our beloved Wigner crystal in a magnetic field. This is at this particular filling. You Fourier transform this data. You can see several features. You can see that these peaks out here are the Moret lattice of the BN. There's no relationship between these. The lattice would rotate as a function of filling. This is one particular filling. And you can see the first order and second order Bragg peaks of the Wigner crystal. As I mentioned, the process of the melting of this Wigner crystal as you go to the filling can be seen in the data. So here is a 0.33. As you go towards this 0.33, you see that the Wigner crystal melts. It re-emerges at higher filling, and then it goes away again. So there are a lot of interesting things in the data. let's first focus on the simplest thing, which is just the lattice constant. So remember, the only thing that this lattice constant depends on is just the charge of the electron. And there is no adjustable parameters. So that's the blue line, okay? And we know what a magnetic field, and then you do the filling, and this is your lattice constant. And I've only put on this picture the places where we both have translational and rotational symmetry breaking. There are places in between where sort of rotational degrees of freedom seems to be melting because of disorder. It's pinning itself to this, whatever disorder you have in the sample, even how little it is, it still pinning. And it melts away as you go towards these incompressible states. So you can compute from the data the structure factors of the electron density of states. So if you do that for the incompressible state, you get nothing. And then you get a beautiful Wigner crystal. And what's interesting is the places where you go near the incompressible states. So, question.
First of all, it's beautiful data. Thank you. What I wanted to ask is, previously you told us about the importance of strain, but here it looks very, very regular.
So the only thing that's important here is the defects.
So strain, even if you have strain, it won't play any role.
This crystal doesn't care about the lattice. It's on a much, much larger scale. The size of this field of view. No, thank you. I mean, you
So
know.
it doesn't matter if you're.
So the lattice constant here, the smallest we measure is 30 nanometers, 300 angstroms.
I see.
So
Doesn't-
it's a giant lattice
All
constant.
right, thank you. That wasn't clear to me.
Yeah. That's right. The lattice just doesn't matter. Okay. So what I was going to get at is these points near the 1/3 and 2/5 states. If you look at the FFTs, you would see signals that look like this one. It will have a liquid looking like the features in the data. It has a characteristic length scale and no orientational degrees of freedom, which in the structure factor just comes up as a ring. And what's interesting is that this Q vector describing this ring is the same Q vector that you would have if you had a Wigner crystal at that density, even though you don't have a crystal. You have something that looks like a liquid. So I thought this was a mystery, but then I was talking to Bert Hauptmann and he said that's the only thing that's not a mystery. It's like, because if you go back to these old papers and compute the structure factor, which have computed the structure factor for the fractional Hall effect, they will tell you that it has a Q dependent signal, the first feature of which is near the Q of the Wigner crystal. So a Wigner crystal and a fractional Hall effect are not that different in terms of the structure factor, except one, of course, is ordered and Q hits has a minima, it's 0. And it could be that we cannot measure between the two blue dots here is because we're really in the incompressible state, where we are in the blue dots, we are on the plateau, but away from the incompressible state.
So it's not a feature of the lock-in state, it's a feature of something near.
No, an off-phase state will have this feature.
I see.
That's what those papers talk about.
Okay.
Actually, they start with basically the fractional Hall.
Okay.
It's actually a kind of a beautiful paper.
So why do you have no feature in the thing on the right-hand side of the block?
This one, the point is that this is inside the incompressible state, so the experiment may be compromised. The liquid is incompressible, but you're just at the edges of the plateau where you can add quasi-particles. The gap is kind of collapsed, but you still have a quantized Hall conductance then. You tell me when I should, I can just keep talking.
Well, here's the thing. We're now into 20 minutes of questions. Okay. So
I have like a few more slides and then I'm done.
okay, maybe that's the natural thing.
And then sorry, it's you give me an hour, I'll speak for an hour. So another interesting thing we found was that as you reduce the magnetic field, the same field of view, which reduces the strength of the Coulomb interaction in this problem, you go from a Wigner crystal to a strike place. And what's curious, and this stripe phase actually, its orientation can change. This is where we know that the lattice has no importance, and it shows very nice one directional degrees of freedom. And again, its Q vector is that of the Wigner crystal, okay, which is quite interesting. So you might ask what's going on here? Why you get your, this is in 0th Landau level of bilayer graphene, why you getting stripes? We thought stripes were observing higher Landau levels. Here in bilayer graphene, n equals 0 and n equal 1 are very close. So you can have Landau level mixing that could become enhanced at low interaction strength and low magnetic fields, which might be the reason why the stripe phase is favored in this problem. So there is some new papers by Alan McDonald and others trying to understand this thing. Okay, so I'll finish with this. So I asked my students, what the hell are you looking at when you're doing this experiment? There is this feature that looks like a ball, and you measure the distance between the balls, and it looks like, yeah, that's your localized electrons Wigner crystal. But first of all, you could ask, how is this even possible? You have a crystal of electrons and you're measuring it using a current. How does this even work? I don't know the full answer to that, but this might offer a bit of clue. So if you look at these images and you ask, what is the size of the object I call an electron? It has a finite size in the picture. And you can fit this size with a Gaussian and extract a sort of a root mean squared spatial size, and measure it as a function of electron, the density of the electrons are measured as a function of magnetic field, the magnetic length. And you'll find that this is the fitting to this Gaussian, this is the sigma. And you can see that as you go to higher filling, there's sort of a saturation. You can kind of understand why sigma gets larger at no filling. Electrons have more space. There's nobody around. They will spread themselves out. As they go towards very dense lattices, they don't have much space. They repel one another. And it's probably best to think about this as sort of a phonon mode of some sort of an electron lattice. And in fact, those dashed lines that you see are if you assume like the 0-point motion of this Wigner crystal lattice with this magnetic length of LB. Square root of 2 LB is roughly, you have 2 phonon modes. It gives you apparently this sort of roughly, you can think of that's if the electrons are just shaking because of the 0-point motion. Interestingly, if you take this this sigma and normalize it by the lattice constant, you get something like 30%. So what does this mean? It means that you have a lattice in which the electrons are localized, but they're exploring 30% of the lattice constant all the time, at least according to these images. And that's large. So one of the things that are of that order are quantum crystals, like solid helium-4. You ask what is the de Broglie wavelength of helium if it's you sit inside a crystalline lattice of helium, crystallized helium-4, it has about this number, this ratio is about 40%. And this is kind of cool. And this might explain why we are imaging these things. Electrons are kind of tunneling between these sides of the Wigner crystal all the time. So you get one more, it doesn't matter. Just find its way out. That might be what it has to do with. Or the other way, which again, we don't know anything about spin. It could be that the Wigner crystal is spin polarized, but we can tunnel in the other spin, and it can tunnel away to the contact is not a problem. So these are all things to be still understood. But this is way beyond the Lindemann criteria of the melting of the crystal. But it's
Can you remind us what the Lindemann criteria is? Is it about 15%?
15% or something.
Question, I was asking about this. These are coming from a Landau level, so there is a Chern number. So a priori, I would have thought that you cannot linearize these states, and it's not obvious to me that you even can fit it to a Gaussian something. Or is it too naive?
Okay. Let's see. I have never thought about the Chern number in the context of the Wigner crystal. Certainly, you have a Landau level. you're partially filling it. Okay, now hold on a second. So this is not a churn insulator. This is an insulator where you're filling a churn band, sure, but it's not like you have a churn gap.
But I thought I cannot take, the eigenstates.
So that's when you fill a churn band. If I like theorist here, no, maybe incorrectly. You fill a churn band if you try to explain the insulator as some sort of a state. But I'm not really sure. Something maybe discuss over coffee. All right, let me show you one other
Time to wrap up.
the final thing. And we are studying, so now we have the opportunity also to study fractional quantum Hall states locally. And one of the things that we have found that's quite curious is this. It's actually was anticipated, but we didn't know about it. So here's a n equals 0 lambda level. You go into the half. There is no quantum Hall state, fractional quantum Hall state there. You do spectroscopy. You see what I call the Coulomb gap. Everybody got to get out of the way to add an electron. This scales with the magnetic length. You can check that. You go into the Laughlin slate. This is the 2/3 state, and you add an electron. So normally you would think, I had a correlated state. There's no overlap between an electron and whatever collective excitation or the quasi-particles of this collective state is. You do the experiment, and you see a very sharp peak. So it turns out that this was anticipated by Jane, another Jane, which is that what this process he thinks it is an electron that goes in, and in the Laughlin state, you have 3 quasi-particles. They can make a bound state. And this bound state of the 3 quasi-particles looks a lot like an electron. And this overlap of an electron to this bound state is a way for you to add an electron to the system. So this peak may be a production of a breaking of electron into 3 quasi-particles, which would be quite exciting if we could, kind of study it in more detail.
So all of the peaks have such an explanation.
So there is a couple of papers online now, but based on these measurements, that they use this composite fermion picture to think about these things kind of being related to some objects associated with what you're making. So there are many possibilities. Again, this is sort of the beginning. Okay, so I'm done. I told you about Wigner crystal stripes, fractional quantum Hall. Let me tell you who did all the work. This troops, they developed the ultra clean in the middle of COVID. Zhao Meng is at Cornell. Galala is working at Apple, I think she's working on iPhone. So Cheng Li has gone into finance, making money. These guys did all the Wigner crystal work. Yuan did all the fractional quantum Hall work I told you about together with Yan Chen and Min Hao, and these guys have done. And we worked very closely with Zlatko and Mike and their students. And the work that I told you on magic and graphene, Kevin, who is now at MIT as a Papalardo Fellow, led this work together with Ryan, and Tomo was a student of Mike who did a lot of the work in analyzing the data. Nicola and Andre, together with Dimitru and Jonah, did a lot of other calculations for producing the states we have looked at. So thank you very much.
So we have time for 10 minutes of questions, and let's start with the guys at the back.
Thanks for the talk. So in the Kekulé state, is the vortex anti-vortex separation set by the strain?
Actually, I don't know. In fact, what we challenge the theorists to do, which they haven't done yet. I don't know whether somebody involved in the theory work is here. It's actually careful. Is to just do many calculations for different strains, see how these things change, and I haven't done that. I don't know.
Okay, and then a follow-up. Even when there's 0 strain overall, you might expect some local strain. Do you see any of these vortex anti-vortex pairs like locally, even if there's no overall?
Yeah, I guess when I say when we define strain, we look at a field of view and we see all the triangles are sort of tilted. What you're thinking of is very dramatic strain, like it's sort of a dislocation or something. We stay away from those areas for now. Okay, so we're looking at like, okay, low strain here, high strain here, we take a whole thing. But yeah, I think, so, I mean, we did this other work on monolayer graphene, where I talked about calculator. In that work, this is published. We found, we did a charge impurity in the set. We found charge impurities by accident, by chance on the sample. And we found that those create what they call Meron, anti-Meron pairs. And you should look at that paper if you're interested, because it actually shows very nice connection to things you would expect. And so that looks like, that makes these kind of measurements possible to extract it.
Satora.
Yeah, thank you very much for very nice. So the weakness crystal, you know anything about swings? You mentioned.
No, so we haven't done any spin polarized measurement. These are just very high field, so I presume they're spin polarized. It's 14 Tesla.
Just ferromagnetic.
I presume it. I don't know for sure.
Andrew.
So there are elements in your answer to the previous two questions that answer mine or allude to mine. So in the quantum Hall, in gallium arsenide, when you have a charge deformation, you automatically get a spin deformation or pseudo spin deformation. And perhaps when you say Meron, you're talking about such a deformation. Do you see evidence as you approach your bigger crystal that there actually is spin and pseudo spin or Rayleigh index textures?
Yeah, so we have some data, but we're not prepared to present it. We're working on just this question because we can't measure spin. It's very easy connecting the two parts of the talk together. We are measuring value degree of freedom. And in the second part of the talk, we ask, does the value degrees of freedom have some correlation with the regional crystal? And the answer is there are such information. So they call it skirmion lattices. Yes. So these are things that are potentially could be seen in our film. And I think the conditions for that may be you not in the data set that I showed you because you're in the n equals 0. If you go to the n equals 1 state, you can see other Wigner crystal states, and those may have a value.
So the skirmion lattices were seen in the conventional quantum ball and something similar.
Okay. So so in a sense, the experiment we did on graphene is related to very much what was done in quantum Hall in the pseudo-spin language.
Yes.
So that would be, but in terms of observing a lattice, the second part of the question, I think that hasn't been done yet, and that is possible. So you would see some sort of a pattern in real space telling you something about either value coherent or value order, which is changing in combination with the charge.
And something that connects, I guess, in that case, the electronic states are described by simple analytic functions, and indeed the fact that you get such a broad spread of the charge density of the electronic charge density, say, in the crystal, maybe fit by this contemplative geometry.
Yeah. So you're saying, to create an electron, you got to create the skirmion. Yes. And the skirmion has a finite size, and so on. Fair enough.
Hi.
It's a very nice talk. Yeah. So actually, I have two comments. One is about the superconducting part. So the superconducting part is a phenomenon you described as a gap much larger than TC, and the gap survival above the transition temperature. That is actually good consistent with common power simulation. If I use a McDonald's model and put in a traction by hand, I've heard quantum power simulation actually exactly the same. Yeah.
Okay.
Right.
Yeah, I didn't know that. I mean, I think the question, I guess, is what are you putting in by hand? V-wave gap.
Oh, just putting in by hand intra-value attraction.
Oh, I see. Okay.
Right. So it's basically so we should put in a positive attraction because Poland is dominating. But if I just flip I just put a attractive function there, and that's what happened. And the quantum power simulation, it happens on both sides problem. So if I have similar system very nicely and by that temperature, and it shows exactly the same quality.
Okay.
And my second comment is about the fraction quantum or the Lockman state about this density oscillation. So for the lock state to see this density oscillation pattern, what I need to do is to go close to an impurity.
Well, that's what these pictures are.
That's right. That's
So,
right.
so they're not too close,
That's
but they're
right, that's
close
right.
enough.
That's right. So I was thinking if you want to see this exactly at Western theory, one may need to change the region a little bit to make the impurity more in the center of your
No. The problem is not the location of impurity because the images of those ringings are taken in the same area where when you go to the 1/3 state, there is nothing to see.
Right. So the 1/3 state is oscillation amplitude actually decays exponentially at the distance to the impurity.
So if you look at these pictures, you can kind of say it's not exponentially decaying, but
Right.
you can kind of say that it's getting weaker,
I see.
but there is some correlation with the impurity.
Any question about the last bit on the fracture maybe if you go back there. So I've recently seen a theory talk on this, and particularly it was suggested that so there is a finite width to all of these peaks, even at 0 temperature, and moreover there's actually an asymmetry in theory between if you zoomed out a little more. So I was wondering if you have more peaks, and also if you can comment about temperature dependence of these widths.
There are more peaks. We haven't measured the temperature dependence. You have no idea how much trouble we're having with this paper. The quantum Hall community is like, how is it possible? You tunnel into a quantum Hall state. It's just not possible. And you show them calculation and you show them this, and like, it's not possible. We measure transport. You go away. We're having a hard time. It's quite funny. We measure the gaps as a function of filling the fit theory because you can just have a sequence dependence of these things, and they just don't want to believe it. It's not possible. So we're having a hard time. So we are kind of like trying to get this published and then go back and measure these stuff.
So the disagreement is whether or not there really is a composite
No, so actually it's interesting.
in tunneling.
No. So the criticism is the following. You have a gap state. How is it possible that you can just connect charge, send charge to the electron? Sounds very reasonable, right? So we went and did all these experiments where we vary the junction. So you would have a voltage division between the tip and the sample, and inside the sample is an insulator. You would have these peaks move as you sort of adjust one of the resistors. Basically saying the voltage is not really representative of energy because you have a resistive sample. So it turns out that this doesn't change at all. And the way to understand it is to think about making a very hot quasi-particle excitation. And that actually has a real meaning in this problem. So that makes it, experimentally, you would think that there will be a lot of problems with this experiment, but it turns out that there is.
But yeah, I mean, I don't see the difficulty. Once you're above the gap, you can surf electrons through.
That's right. So this is the difference between zero bias and a very highly excited state, which is never really usually studied.
I think they just need to get used to thinking about spectroscopy. I mean, this is a little bit done on quantum Hall systems.
That's right. So optical spectroscopy is done a lot.
You
And
can tunnel into an insulator too, right? You just put a big enough voltage on the system.
I mean, supposedly.
well, it turns out in this system, actually, when you tunnel into it, it actually has a lot of really meaningful things. Like, for example, in the integer quantum Hall state, when you tunnel inside the gap, you actually are connecting an electron, you're making an exciton. And and there is actually quite an interest. If you put a little bit of hole in it, the electron goes in and pairs up with that hole that's there. So there's actually quite a lot of interesting physics having to do with tunneling into these states that are just not ordinary insulators.
Just before we end, I think Chairman's prerogative to take you back to the very beginning of your talk,
Yes.
and when you had the cascades. And my question was, you have a fantastic atomic resolution here. So you can actually look at whether the lattice deforms as you add electrons, as you change your filling factor. Do you see any sign of any deformations as you change filling factor? Or is it
If
just
something is
completely
changing as we're tunneling, it would be very hard for us.
No,
to
I
see.
mean, you can gate the system so you can go from for 0 to 1 to 2. And as you do that, you're adding more electrons into your Wannier states, right?
Yeah, I think the problem, Pierce, is that what we measure is the entire thing, the electron and the lattice. So if the lattice is changing and the electronic state is changing, we will have a hard time to say which is which. Because you're looking at the density of states which will be affected by both.
But you could see the movement of the atoms. if they were to move.
I
at
mean,
all.
this is, this is high resolution, but it's not X-rays.
Okay.
When you're doing diffraction, and you can get very precise, 1% change of the lattice.
You couldn't do it.
Yeah, you see, if it's 5%, yeah, but
I see.
that would not happen.
Yeah, got it. Thank you very much. Well, let's thank Ali for the
Thank you.
great talk. We have 20 minutes before Amalia's talk, so downstairs is in the cafe. if you'd like to go.
Thank you.